we were talking about, no, I can take it off now. So we were talking about the solution of equations for solvability by radicals. Let me briefly review the statement. So we had said that the field extension L over K is called a radical extension. If we have a chain of intermediate fields, so L, the last one, contains n minus 1, contains L0, which is K, of intermediate fields. Such that each is obtained by just taking a root, an nth root of something. So for such that for all I, we have that Li plus 1 is equal to Li into at some element Bi, where with Bi, the root of the polynomial. X to the mi minus k with a in the previous field. So ai. Okay, and the polynomial f in the x is called solvable by radicals. If there is a radical extension of K, if there is a radical extension over K, such that F splits over F. And now the statement was that that we are trying to prove the theorem of Galois is the following. So theorem Galois. So
yes. Professor, excuse me. Yes. We cannot hear clearly.
You can't hear me?
Yes.
I'm not quite sure what to do. Here's the microphone. So
yeah.
So I'm not precisely, there's not very much I can try to speak as loud as I can, but I don't know precisely what it depends on. So this, you couldn't hear me there, or you can't hear me here?
We can hear you now, but we couldn't hear you there.
Okay. Yeah, well, I'm not. Okay, so I will try to speak a little bit louder, although I do already speak rather loud. So let K be a field of characteristic 0. And so then F is so, and F is polynomial with X. So F is solvable by radicals if and only if the Galois group of F is solvable. I will not review the definition of solvable group. Is solvable. So there's if and only if. So we will show the, in some sense, more important part, this, that if f is solvable for radicals, then the Galois group must be solvable. If there's time at the end, I will make some remarks about the other direction. As a step in the first step in the proof, it's already mentioned, we need to prove the following result, kind of more technical, that we can reduce to the case that the in this chain of intermediate fields, the last one is Galois over K. So let K you here the frequency 0. Let L over K be a radical extension. Then we can instead, we can extend L further so that the bigger field is both radical and Galois over K. So then there exists a field extension L prime over L such that L prime over K is a radical Galois extension. So now I will try to prove this theorem. So if you can't hear me when I speak here, you tell me and I will only talk there, but it would be a little bit unpractical. But if that's the way it is, then that's the way it is. So we want to prove this now. This is not trivial. So it's a kind of reduction step, because here, if f is solvable by radicals, it's not required that this radical extension over which f splits is also a Galois extension, and we want to be able to make this additional assumption. So proof of this theorem, this second one. So we make an induction over the degree of L over K. So the beginning of the induction is kind of trivial. So over the degree of this grid. So if the degree of L over K is equal to 1, then L is equal to K, and we can take also L prime equal to K. It just means that the polynomial that our radical extension was just K itself, that's the radical, and then we can do like this. And certainly K over K is Galois. So now we assume that the degree of L over K is bigger or equal to 2, and we assume that the theorem is true for all extensions of smaller K. For all radical extensions. Of smaller. So now we use that we have a radical extension, so it's given by a chain of intermediate fields. So as L over K is a radical extension, we can find an intermediate field, just maybe second to last step, find an intermediate field. Of this extension, so which is different from L, and such that L is obtained from F by adding the root of an element. So such that L is equal to F of B with for some element B in L, and there exists in N a positive integer such that B to the N is in F. No? We know that being a radical extension means that one get from K to L infinitely many steps, where each time you add a root like that. And so we just take here the last step. And now we want to prove it, prove the induction step. To prove it for L from no infinity. So by induction, we know that we can do this now for F. So by induction, there exists, certainly we know, so as F is different from L, the degree of F over K is smaller than the degree of L over K, so we can apply induction. So there exists a field extension F prime over F such that F prime over K is a radical Galois extension. Okay. So, as this is a Galois extension, we have that, so in particular, it follows that F prime is the splitting field of some polynomial with coefficients in K. Okay. So now we look at the Galois group of this. So we somehow now have to find, use this situation to somehow find an extension of L prime, which somehow takes into account this F prime, such that we get a radical Galois extension. And we do this in a slightly tricky way. So we look at the Galois group of F prime over K, and we write down a polynomial. So we put G to be the following polynomial that is the product. It's a bit similar to what we did also in the proof of the fundamental theorem of Galois theory. Take the product over all elements G phi in the Galois group. X to the n. So the n is this n here. We have to exist in n with that. So x to the n minus phi of e to the n. Note that phi to the n is in F, and therefore in F prime. And if I apply an element in the Galois group, I stay here. So this makes sense. Polynomial with coefficients in F prime, even though B itself need not lie in F. Okay, so we take this. And so what can we say about it? So what do we want to use it for? So the first thing that we notice, if we apply an element in the Galois group of F prime over K to it, we just, as in we also did this before, we just reorder the factors. So that means if I apply phi to the coefficients of this polynomial, I get the same polynomial, which means this polynomial is a polynomial with coefficients in k. So G is invariant under the gallows of f prime over k, thus G is a polynomial with coefficient in k. Okay, I've written it down in this form, but the whole product is a coefficient in k. So now we look at the splitting field of this polynomial, and this will be our answer. So let L prime be the splitting field of G over K. Right, maybe over F, just to be on the safe side. Okay. So we take this over F, then I claim if I also have that L prime is the splitting field of just F times G. So where did I have it? So we have that F prime is the splitting field of some F into X, and so the splitting field of F times G over K. So this follows essentially from the definition of splitting field. Clearly, F splits over over F prime. This thing, so maybe we should say a few more things. So maybe I say one more thing. So I take the splitting field of this, but we can assume no, I take the splitting field of F prime, so that's all that I do. That's what we conclude. So I take L prime, the splitting field of this over F prime, and then I claim then L prime is the splitting field of Ft over K. So this follows, as I said, from the definition of splitting field. Certainly F splits already over F prime, so it splits over an extension of F prime, so over any extension of F prime. And also G splits over L prime, so F times G splits. On the other hand, if one is in the splitting field, then if F times G splits, then both F and G have to split. So one must contain the splitting field of F, and over the splitting field of F it must contain all the roots of G, and so it will be the same. Anyway, so if you just think of it by definition, you can discard the splitting field like this. So the splitting field over the splitting field of something else is the splitting field of the product over the original field. That's an easy exercise. So therefore, is a Galois extension. We want to show, according to our theorem, that it's a radical Galois extension. So we also have to see that it contains L, or at least we can choose it to contain L. So furthermore, we have B is a zero of G, because if I take P to be the identity element in G, then one of the factors here is x to the n minus b to the n, and the root of that is b. And so this is a zero of G, so thus P is an element in L prime, and so as F is contained in L prime and B is an element L prime, it follows that L, which is equal to F of B, is contained in L prime. So we have an extension of L prime is indeed, as we require, an extension of L. And now we have to show, the final thing we have to show is that L prime is a radical extension. Well, and this follows from this crazy definition in terms of G. So why is that? So L prime over F prime is the splitting field of G over F prime. No, but I think that's how we define it. So therefore, this field extension is generated by the zeros of G. So if we just add the zeros of G to F prime, we get L prime. But now we have to see what the zeros are. So, and if we take, so, and for every root alpha of G, we have by definition that we have that 0 is equal to the product over all p in G of alpha to the n minus p of p to the n. So that means it must be, if it's a zero of this product of polynomials, it must be a zero of one of the factors. So it means we have alpha to the n is equal to p of p to the n for some phi. So that, well, now I can work this out. So thus there exists the P in the variable of F prime over K, which was G, with the alpha to the n is equal to P of P to the n. And we know that So b to the n was an element in f prime, and so this is also in f prime. And so we see that every element we add when going from f prime to L prime is the nth root of some element of f prime. So this is a radical extension. Okay, so this was this reduction step, and now we come to the actual proof of the one direction of the theorem. So the proof. So now we want to prove. So what here I would note like this. So that means if okay, so what I write it out, f solvable by radicals implies that regardless of what f is solved. Okay, so now we have to do this. So we first remind ourselves what it means that f is solved by radicals, and then we will work on it, using the fact that we know that if we have enough roots of unity, then adding an nth root of something is given by the Galois extension to be in Galois. So let f into x is solvable by radicals. So that L is a splitting field of f of k, then it follows that the Galois of f is equal to the Galois of L over k. And we will want to show that this group is solvable. Okay, so let's try. First, write down what it means that f is solvable by radicals. So as f is solvable, so there exists a chain, a sequence of fields. So K, so our ground field is in K1. Contained in K2, which is K of alpha 2, some element alpha 2. This is contained in K3, equal to K of alpha 3, and so on. Kn, which is K, not K. So this was K1. So this is K or equivalent to 1 of this. This is K2 of alpha 3. And this is Kn minus 1 of N. For each of them is just a radical of things before. So where such that, and this Kn, okay, such that for all I, we have that there exists and Ri bigger than 0, such that if I put Ai to be alpha I to the Ri, this is an element in Kn minus 1. No? So we have this chain of fields, one contained in the other, so that each one is obtained by the previous one by adding the Rith root of some element from the previous field. And obviously in the last field, we must be able, this polynomial must split. So, and f splits over the n into linear terms. And by what this thing I just proved, this reduction, we can also assume that Kn over K is a Galois extension. We can assume that Kn over K is a Galois extension. Okay. So now, in order to find something out that these relative Galois groups are abelian and so on, this was always under the assumption that the field, the smaller field, has enough roots of unity. So we have to make sure that we have enough roots of unity in the business, so we'll add them to K. So let me do this. So let M be the greatest common multiple of all these numbers. So the way I counted it here, it starts with 2. So of R2 until Rm. I take the greatest common multiple of them. So, and we choose a primitive mth root of unity. Psi be the primitive mth root of unity. Then we can get primitive Rith root of unity by just taking a suitable power of this. So then if I take psi to the m divided by Ri, this is a primitive Rith root of unity. So thus, if we add this psi for our K, this new field will have all the roots of unity that we might possibly wish for. So let F to be K of psi. So then F contains all primitive Rith roots of unity for all these Rith. So then F contains primitive Rith roots of unity for all R. No, for I from 2 to n. Okay. So now we change here, we replace K by F, and then we make the same extend chain correspondingly. So we put F0 to be our K, F1 to be F, so we have one more step in the beginning, and we put Fi for in bigger I to be fi minus 1, to which we add the same alpha I as before. So then we get a nice chain. So let's get it. F is contained. Yeah, first I just write this. So K is contained. Okay. So F0 is contained. F1 and such that at each step we have just added some root of something. So we know that Kn equal L Kn is the splitting field. So the Kn here, because this was, we could assume that Kn over K is a Galois extension, so Kn over K, Kn is the splitting field of some polynomial distributions in K. Kn is the splitting field of some polynomial say G in Kx. And so, by the same argument I already used before, we have that Fn is the splitting field. Say of x to the m minus 1 times G over K. No? Because again, we want to just add in addition the roots of the mth roots of unity. So this gives us, if we add one primitive mth root of unity, we add all of them, so we get the splitting field of this, and then to have the splitting field of something over something over the splitting field, we can just take the splitting field of the product. That's how I explain. Go. So we have this. So therefore, also Fn over K is a Galois extension. And thus also Fn over Fi is a Galois extension. For all I. Because Fn is a splitting field of this polynomial over K, so it's also a splitting field of the same polynomial over any intermediate field. And being a splitting field means it's a normal extension, and the characteristic means it's a Galois extension. So now we know that F1, which is F, and therefore all Fi which come later contain all primitive Ri roots of unity. Contain primitive Ri roots of unity for all I. Then we know that if we just, and we have now just Fi is just F alpha I minus 1 added alpha I, where alpha I is an Ri root of something. Alpha I is in I minus 1. So we can apply this theorem that Fi over Fi minus 1 is a Galois extension with abelian Galois group. So that by this theorem is a Galois extension with abelian Galois. So now we are kind of getting close. So also F1 over F0 is a Galois extension. With a abelian Galois group. Because F1 is equal to F0 theta for primitive mth root of unity. And we know that if we add the primitive mth root of unity to a field, this gives us a Galois extension with a abelian Galois. This was another theorem that we proved together with this one. So, now we can put this together. We look at the kind of second part of the fundamental theorem of Galois theory, which relates normal subgroups of the Galois group to the intermediate fields, which are normal over the base field. So by the second part, of fundamental theorem of Galois theory, we have what? We have that so the Galois group of Fn over Fi is a normal subgroup of the Galois group of Fn over Fi minus 1 for all r. And we know that the quotient is the Galois group of Fi over Fi minus 1. So that's the group. And if I take the Galois group of Fn divided by Fi, it is divided by the Galois group of Fn. And now it's slightly wrong now. Yeah, take this Fi minus 1 by Zn of I. This is equal to the Galois group of Fi over Fi minus 1. No? That's how we L. Right? This. And this Galois group, according to the story, is a B, which is a B. So we can just put it now together. So thus we have the chain so we have the Galois group of N over K contains the Galois group of N over F1 and so on. The Galois group of Fn over Fn. Yeah, because these are the automorphisms of F which fix K. The subgroup of those are those which fix the bigger field F1 and so on. So we have this chain of subgroups of the Galois group of Fn over K, and we know that successive ones are normal in each other with the Being quotient. So this with Galois group of Fn over I plus 1 over Fi normal in the Galois group in Fn minus 1 with the Being. But this is precisely such a subnormal chain which establishes that this Galois group of Fn over K is solvable. So this thing, this chain makes clear that the Galois group of Fn over K is solvable. So that's already an achievement. So we find that the Galois group of this extension is solvable. Unfortunately, this is not directly what we are supposed to show. We are supposed to show that the Galois group of L over K is solvable where L is the splitting field of our original polynomial f over k. So far, that's to show that the Galois group of L over k with k and splitting field of f is solvable. So we have to find a way to get from Fn to F. Or the Galois group of Fn over K to the Galois group of L over K. And that's actually quite simple. So we need to go back from F to F. So L is the subfield of Fn, or at least you can choose it to be a subfield of Fn, because X splits over L and also over Fn. and L over K is a normal extension. So we can apply again the second part of the fundamental theorem of Galois theory, which says that Fn over L, so the Galois group of Fn over L is the normal subgroup of the Galois group of Fn over K. That's my second part of the fundamental theorem. Of Galois theory, we have that the Galois of Fn over L is a normal subgroup of the Galois group of Fn over K, and the quotient is the Galois group of L over K. So this in particular means, not L over K, so this means in particular we have a surjective homomorphism from the Galois group of Fn over K to the Galois group of L over K, just the natural projection to the quotient. Homomorphism of groups from the Galois group of Fn over K to the Galois group of L over K. But now we are done, because we know that if we have a surjective homomorphism from a solvable group to another group, also that group is solvable. Is solvable. And that's what we have to show. Okay, so this is this theorem of Galois, which was a high point of mathematics at the beginning of the 19th century. So the proof is, in some sense, it's a bit technical, but so many of the ideas are, it's putting things together. So we have the main ingredients is that we know that if we have in our ground field enough primitive roots of unity, then adding an nth root of an element from the ground field to the ground field gives us a field extension which is Galois with a being Galois. And so we do this thing that if we have this chain which makes us a radical extension, we add enough roots of unity so that we have always enough roots of unity, and then each step in the chain after doing this will be a Galois extension with a being Galois group, and that then just means that on the level of Galois groups, this chain of field extension will instead give a chain of subgroups which makes this corresponding Galois group solvable, and then apply this fact that under homomorphism, the homomorphic image of the solvable group is solvable. So that is this theorem. And so, as I mentioned, if you have it's a well-known, so one can prove, it's not difficult to prove but not also completely easy, that the symmetric group in n letters is not solvable when n is bigger or equal to 5. So we have to not the smart if n is not solvable. If n is bigger or equal to 5. So thus if f say in X is reducible of degree n with divergence of n, then f is not solved by radicals. So this is a very nice fact, and one can show in a suitable sense that the general polynomial will have of degree n will have the property that its divergence is Sn. Now, however, I want to use this result to give you at least a way to find many examples of polynomials which are not solved by radicals. Namely, by showing that under certain conditions which are easy to check on the polynomial, the Galois group will be Sn. And this is the following. So basically, how to see whether a given polynomial is solved. And I can give you, so we give a criterion, a sufficient criterion for polynomial of degree p. Of degree p, so p a prime number, to have Galois group S. Okay, let me do this criterion and you can check it basically in terms of, say, high school calculus. So it's the following theorem. So let P be a prime number. And I take a polynomial with coefficients in Q. So let F a polynomial with coefficients in Q, which is irreducible. For Q, obviously. And of degree p, and assume that f has precisely p minus 2 real roots. P minus 1, 2 real zeros. So that means there are two, so over the real numbers, this polynomial has p minus 2 roots. Okay. So then the Galois root is SP. So as corollary, if P is, if we make the same assumption and P is at least 5, and the same assumptions, if P is bigger than 5, then F is not solvable by reference. Okay, so let me, and then afterwards we see that it's very easy to make examples for this, and it's very easy to check this, obviously, by some elementary curve discussion, like one does in high school. So now let's try to prove this. So it's, in Ipora, it doesn't seem to be very clear what anything has to do with anything here. So what should one care about the fact that this has p minus 2 real roots? Why should this have something to do with the Galois root being SP? So we just try now to analyze what's going on. So obviously this game is irreducible and it splits over the complex numbers, so therefore all the roots must be different because we are in the separable situation. So let sigma equal to A1 to AT be the set of roots of Fx. And I number them in such a way that the first two will be complex, so not real, and the other ones are real. So with A3, A4, and so on, until 80 in R. And we know that and A1, A2 are elements in R and C, which are not real, and they are complex conjugates. We have seen that before. Okay, now we want to study the Galois root of this thing. So the Galois root of F is the Galois root of the splitting field. Obviously, we can choose the, it would just be the field generated by the root, so we can take it as a subfield of C. So that L contains C, the splitting field. Of F over Q. So then, by definition, the Galois root of F is equal to the Galois root of L over Q. And we know that for such a polynomial, the Galois root of the splitting field is a subgroup of the permutation of the roots. So, and we know the Galois root of F is the subgroup, or isomorphic group, but I think I write this subgroup of the symmetric group on Z, which is isomorphic. So, symmetric group in P letters. So we want to show that it's not just this, that this subgroup is actually the whole group. And so we somehow have to find enough elements in it on the basis of the information we are given to fill up the whole group as P. So first, as F is irreducible, if I take, say, Q A1 over Q, so the degree of this quick extension is equal to the degree of the polynomial, so it's equal to P. This simple algebraic extension is P. So thus, as L over K is a Galois extension, we have that the number, that the Galois group of F, the number of elements in the Galois group of F is after all the same as Galois group of L over Q. And this, by the degree theorem, is equal to the degree of L over Q. So this is equal to the degree of L over Q because of the Galois extension. And then by the degree theorem, this is equal to the degree of L over Q of P1 times the degree of QA1 over Q. And so degree of QA1 over Q is P, so this is divisible by P. With P. The number of elements in the Galois of F. So we know by Cauchy's theorem, if a prime number divides the order of the group, then that group contains an element of order P. There exists an element rho in the Galois group of F of order P. Okay, now it's an easy exercise to see that there are not so many possibilities. You know, if you have in SP, I claim the only elements of order P are the P cycles. So it's very easy, just we must have a proper in SP. Only elements in order P are the P cycles. So, thus, this Galois group contains a P cycle and then contains obviously all powers of it, so it contains all the cyclic permutations of A1, so A0. So we have all the cyclic permutations. And so obviously if we take all the cyclic permutations, there will be, so the group of cyclic permutations, so of say, so these cyclic permutations is a cyclic group. It will be generated by any element which is not a neutral element. So in particular, we can take any power of it, which is not repeat power, and this will still be a generator. And so one power of it will send A1 to A2. So by replacing rho by power, rho to the k, we can assume that rho of A1 is equal to A2. And then, all the other ones, we can choose how we number them. No? I mean, here I've just somehow, these are the real ones. Nobody has told me in which order I have to order them. So now I just say, okay, we have this element rho, and then this element rho will have the properties that it says A2 to A3. So the next, what A2 is sent to by rho, I call A3 and so on. So by renumbering the other AI, you can see that rho here rho of AI equal to AI plus 1 for I equal to 1 and E minus 1 and rho of AP is equal to A1. Okay. And another element in the Galois group that we anyway have is complex conjugation. So we know that the complex conjugation is an element. So tau sends A plus IB to A minus IB is an element in the Galois group of F, because it certainly preserves Q and is a, and so and it preserves also the splitting field. I mean, it sends it to itself. So and so thus we see, so maybe this I call tau, and here we have tau of A1 is equal to A2, because A1 and A2 are complex conjugate, and tau of A2 is equal to A1, and all other ones are real, so the complex conjugation does not do anything to them. And tau of AI equal to AI for I bigger than 2. So if we identify this S of sigma, so S of set A1 to AP with SP, by just saying, permuting A1 and A2 is the permutation 1, 2, and so on, we obtain the Galois group of F contains the element 1, to and so on to rho, to P, so this cyclic permutation, and it also contains the transposition 1, 2. And I claim that's enough, because these two elements already generate the group SP. So enough to show. That 1, 2, and P, and 1 generation. This is an easy exercise, but let me just sketch it. So, for say 2 smaller j smaller than p, if we just see what it does to AI. So if we take rho to the j minus 1 tau rho to the 1 minus j, applied to AI, maybe I want to just I. What is it? Well, this is equal, so I have rho to the j minus 1 tau, and then we apply this. This somehow shifts it by this number, so this is a I plus 1 minus j. If and this is tau now wouldn't do anything to that if we are on the right path, so j minus 1 a I plus 1 minus j is equal to, so this just subtracts this is equal to AI. So this is when? Well, if the tau does not move this element. So if I plus 1 minus j is different from 1 and 2. That means if I is different from j and j plus 1. Okay, so the elements, so this thing will not move AI if I is different from j and j plus 1. And what does it do to AJ? Well, so here this gives us A1, this rho to the j minus 1 tau A1, tau A1 is A2. And now this just means we add this to it. This is equal to AJ plus 1. And in the same way, rho to the j minus 1 tau rho to the 1 minus j, AJ plus 1 is equal to AJ. So thus, this element rho to the j minus 1 tau rho to the 1 minus j is just j, the notation j plus 1. So that means if we have the permutation 1, 2 and the cyclic permutation, we have all transpositions j, j plus 1, and these are easily seen to generate. And so we see that in this case the Galois group is SP. And so let's see, time is anyway almost up, so I can give at least an example of this. I think that this is very easy to check by elementary calculus. So so I had said that if I have an irreducible polynomial with coefficients in Q of degree a prime number, which has p minus 2 real roots, then its Galois group is SP. So let's see how one can check this in examples. If you're given the polynomial, how you do check that this is the case? And this is then very similar to what one does in school. So example, I take for instance the polynomial f is equal to x to the 5 minus 10x plus 5. So it's polynomial equal to 5. I claim its Galois group is S5 and therefore it's not solved by radicals. So by the Eisenstein criterion, for the prime 5, this is irreducible over Q. So now one does some kind of standard curve discussion. So if you take the derivative of it and you put x equal to 1, you find the derivative is 0. And if you take the second derivative, you find that this actually is a minimum. So f has a minimum at x equals to 1. I know this is like one does in school, so you take the first derivative, you have to find the 0 of that, you can easily find the 0 of the first derivative of this thing. At 1, I mean if you just put 1 into the derivative, you get 0, and if you then compute at 1 the second derivative, this is positive, and so therefore you have a minimum. And you can also compute f of 1. And this is equal to, according to me, equal to minus 3, which is negative. It has in the same way, f has a maximum, if I didn't make a mistake, at x equal to minus 1. Again, if you put minus 1 into it, into the derivative, you get 0. Maybe I should write the derivative. Then x to the 4 minus 10. So it's not very difficult to deal with. So f has a maximum at x equal to minus 1. And we have, now it's minus, and we have f of minus 1, this, if I'm not mistaken, equal to 3. I hope that's true. Anyway, it is equal to something which is at any rate positive. And, you can easily see that there's no other point in the real numbers where the first derivative is 0. No? So it's at 1 or minus 1. And so and f has no other extreme values. On the other hand, clearly, if we let x go to infinity, then this term here, x to the 5, dominates. It has a positive coefficient, so we will get that f of x goes to plus infinity. And again, in the same way, if x goes to minus infinity, this goes to minus infinity. In particular, for x sufficiently large, f of x will be positive, and for x sufficiently small, f of x will be negative. So we can make some qualitative drawing. F must somehow very qualitatively look like this. We have here, so this is 0. And so then, so at 1, we have a minimum, and the value is negative. At minus 1, we have a maximum, and the value is positive. For very large numbers, it will be negative, and for very negative numbers, it will be negative. For very large positive numbers, it will be positive. So by the intermediate value theorem, or by the, which one is it? By the intermediate value theorem, it follows that f must have a 0 somewhere between minus 1 and 1. So by intermediate value theorem, f has a 0 in the interval minus 1, 1, in somewhere between minus 1 and infinity, minus infinity, and precisely 1, 0. What's this? And in 1, infinity. And so if there were more, okay, so we have these 3 zeros at least. But if there were more zeros than these, one would have to have another extremal value in between. No? If it goes below 0 with negative slope, then in order to cross again the 0, it must have a minimum before. But it has only one minimum here, only one minimum here. So it has precisely these 3 zeros. And no other. So thus, f is not solvable as it is. Okay, so maybe that's a good point to stop. I essentially used my time and I proved what I really felt I needed to prove. The other direction of the theorem of Galois is a little bit easier. We have done some of the steps, but it would require whatever, another 40 minutes or so, so I will spare it to you. And this is somehow what was the main reason why people studied this problem, to see that not in all cases the polynomial is solvable by radicals. Okay, so maybe I will, if there are no questions, I will stop here, or you can ask some questions. So this is so otherwise it's the last lecture, so I think you still have some tutorials, but that would be the end of the story. I will keep seeing you, but at least for now then lecture is finished, and I wish you a good time over. Anyway, I wish you a nice weekend. Okay, so no question? Okay, so then let me say goodbye, and we see each other later. Okay, bye.
Thank you.
Thank you.